Welcome to Complexity Made Simple. My name is Paul Allen, and before we get into today's video, well, I'm just going to remind you the 3 books that are on sale. Drink tea and read the paper. If you're a green belt and a black belt and you want simple instruction on how to apply your skill, design of experiments for 21st century engineers, and finally, a statistical process control for small batch production. They are all available from lulu.com and the links are in the video below. Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's video newsletter, well, we're going to take a look at Statistical Process Control, SPC. Why should you be using SPC? And as someone who works with clients, manufacturing clients, one of the strongest pieces of advice I could give them is to use Statistical Process Control to understand their processes better. And the basic reason why you're going to use SPC, because you'll make more money if you use SPC. You'll make less defects if you use SPC. Everyone will make better decisions if you use SPC. So let's take a look at the subject, let's introduce it to you, and let's see what will happen potentially if you don't use Statistical Process Control on your manufacturing processes. Now look, your manufacturing processes, if you didn't already know, are big random number generators. So in other words, if you just set them up, take your hands off, and then you measured some feature, some dimension, what would happen if you did that? You'd get basically a random number. So what does a random number generator look like? Well, it sort of does this. So in other words, the process isn't moving. It's not swinging up or down. But you've got that little bit of noise every time you make a part. So for example, if we were molding the top of one of my felt tip pens and we were measuring the diameter in there, of course the diameter would be fixed around some target, but every one of these that we made wouldn't be identical. One would be a little bit bigger, one would be a little bit smaller, and essentially your process generates a random number for that dimension. It's a random number generator. Another way to think of it is it generates a natural process behavior. And some people do call these process behavior charts because that's what they're trying to communicate to you. They're trying to communicate the natural process so that you can make better decisions about your process. So Don Wheeler, if you go and look at books, Short Run SPC is a great Don Wheeler book. So if you go and look at that, he will talk about process behavior charts in that textbook. So you have a random number generator. Of course, the problem with a random number generator, you don't necessarily know what's going to come next, but they have certain features that you can use to understand them. One of the features I've just kind of put on this diagram, they have a signal. The signal is the average. So where's the process sitting? Where's the signal? But they also have another feature, which is the more confusing feature. They have the spread here, which is known as noise. Yeah, you might also look at it as, if you look at it as a basic statistic, it's the range that the process is generating. And these are 2 things that we can take into account from a random number generator. So let's just consider a random number generator that's kind of easy to understand for a second, and we'll use this. We use a 6-sided dice. It's one of my favorite random number generators. I often use them in class so that people can understand processes. And of course, like any random number generator, I don't know exactly what's going to come next. But what do I know about my random number generator? Well, of course, I know the average. So the average on a 6-sided dice, 3.5. So I know the signal. So let's just put that up there. I know the signal for this random number generator. I also know the noise. So I know the range for my random number generator, which in this case, of course, is 1 to 6. That's known as the noise. And finally, there's one last thing that I know about my random number generator that I didn't mention here. I know the shape of the data. I know the way the data is going to come at me. So in other words, for the 6-sided dice, what I know is that if I roll 1,000 times, of course, what I will get is a nice uniform distribution. It won't be perfectly flat. 1, 2, 3, 4, 5, 6. So I know the distribution. I know the way the data is going to come at me. Okay? And they're the three things that I know. That is my process behavior. That's my natural process behavior. And then what we do is we use the natural process behavior to decide if something is wrong with the process. We're not going to use the chart to decide if there's something wrong with a part, by the way. It's not telling me that the part is a problem. It's telling me that the process has a problem. Its behavior has changed. So for instance, if I took my random number generator and I rolled it and I said 7, what would you say to that? Well, straight away, you would know something is wrong with this process, because it isn't what this process does. This process has a range of 1 to 6. It has a distribution that goes up to 6. It's got an average of 3.5. If I start rolling 7s, there's a good chance this behavior is going to change and this behavior is going to change. It isn't what your process does. It's not normal to this random number generator. And just to make the point about the fact that it doesn't grade the part, the spec in this case could be 0 to 8 is perfectly okay. Therefore, getting a 7 in this case, I wouldn't be producing a defect, but the process behavior chart would be telling me something's wrong with my machine. Your machine is deteriorating. It's performing in a way which is not normal to it. And that essentially is what SPC is. It takes a snapshot of natural process behavior. And by the way, the snapshot comes from the process itself. So these aren't tolerances. Any limit that we put, this limit here on this range, this came from the dice. I've got a 10-sided dice here, which goes from 0 up to 9. Clearly, its behavior would be different here. The average is up at 4.5, I believe, and the range is 0 to 9. That would be the natural behavior for this process. And we would use those numbers, those behavior patterns, to judge whether this process is healthy or not. Because that's what it's telling you. Is your process healthy? Is it well set? And is it stable and just producing in a good way? The way it did yesterday and the day before and the day before that. So how will process behavior charts, how will SPC save you money? Well, here's the danger if you don't use them. Let's take the dice here and let's use tolerances instead. Now I'm going to put a tolerance of 1 and 5 on this chart. So in other words, if I roll a 1, I get a defect. If I roll a 6, I get a defect. That's my tolerance. My customer has said, don't send me 1s and don't send me 6s. Now, before I put those tolerances on this chart, we would have been perfectly happy if all these rules had been in play for my normal random number generator. We would have been perfectly happy that my six-sided dice is performing very well. But we tend to use tolerances. Engineers use them, operators use them, technicians use them, because we tend to want to produce good parts. So we're going to use the tolerance to judge what goes on, and we're going to use the tolerance to tell us whether we should adjust or not. Now, if you look at this process, this is set perfectly well. The defect rate, of course, is going to be 2 in 6. It's going to be 33%. But actually, that's the best we can achieve for this process. The natural process behavior for this process is a minimum defect rate of 33%. Okay, and the chart would communicate that. That's what it's trying to do. It's trying to communicate natural process behavior. But we're going to use the tolerances instead. Now, of course, when we turn the machine on, we get lots of opportunity to roll 2, 3s, 4s, 5s, etc. So we get lots of good product and everything's okay. Operator doesn't worry, doesn't make an adjustment. But of course, then the operator gets a 6. They get a defect. Now, when operators see defects, what do they want to do? Well, they want to adjust. What they're basically doing, look, is they are reacting not to the pattern, they're reacting to an individual data point. And that's dangerous, because an individual data point is not telling you whether the process is performing well or badly. But because we have an out of spec result, we are going to react to it. What does the operator want to do? Well, what he's going to want to do, he's going to want to adjust the process in this direction. How much will he adjust it by? Well, he'll probably adjust it by 1, which means now, of course, I can get zeros out here. Okay, so he makes the adjustment. Then he carries on running the process, and of course there's a good chance that he'll have some good product again, and he thinks he's fixed the problem. Then what does he do? Well, now he gets another one, but this time he gets one out here, out at 0. Now what does he want to do? Well, now he wants to adjust it again. But this time he's going to adjust it in the other direction, but instead of adjusting it by -1, this time he's going to go in this direction, +2, which means he can get 7s out here. So look, before we started using tolerances on this process, we had a defect rate of 33%. Now we're using tolerances, and we're allowing the operator or the technician or the engineer to adjust the process backwards and forwards. And they're doing it but from one data point, which is a very bad habit to get into. From one data point, they are making an adjustment. What have they done? They've made the situation worse. They're moving this thing backwards and forwards, and suddenly now we've got a defect rate of 4 in 8 or 50%. Your people are making your processes worse. And this is what will happen if you don't use SPC. Your defect rates will be elevated if you do not use statistical process control. Because what SPC is trying to do, it's trying to communicate the natural picture. Because of course, what an operator sees is a data point at a time. It's a very bad habit to work to one data point. What we want to communicate to the operator is the natural process behavior. And whilst that natural behavior is going on, what will they do? They will take their hands off, they will drink tea and read the paper, because that's the best thing an operator can ever do when they are controlling a process. And that's what SPC helps you to do. Keep your hands off and make more money. Now, of course, the pattern that is happening out on your manufacturing process isn't a uniform distribution. It's typically a normal distribution. And maybe you've got this situation. And of course, what the operator will do, look, maybe there's 2% defects in that tail, 2% defects in that tail. what will they see most of the time? Well, most of the time, they'll see good results because there's lots of opportunity to produce good results. What will they think they've got? They won't think they've got the black distribution, they'll think they've got the red distribution. But then, of course, there's time when you have to get one there. Now they believe the process has moved when it really hasn't, because they don't understand the signal and the noise coming from their process. They don't understand natural process behavior. So SPC, what's it for? Well, like all of these things, I want you to make more money. I want you to smash the hell out of your competition. Take the equipment that you've paid thousands and thousands of pounds for and get the most out of it and smash your competition to pieces. The best way to make more money, one of the best ways, is to use statistical process control. It will guarantee you get the minimum amount of defects from your process. You don't over adjust the process, and you will make more money. Use SPC.